Okay, today we're going to be looking at stellar evolution. So what does that mean? It means how the star develops over time and how it changes. So if you were to look at stars, they first appear to be white, but if you look a bit closer, you see you'll see some stars are a bit red or blue. Some are really quite white and some are a bit yellow. The colour of a star is related to its surface temperature. So if you were to heat a bar of iron in a furnace, you would see it started to glow red. If you got like a really powerful blowtorch and kept heating this iron, it would start to glow white. The different colour that the iron would be glowing is an indication of how hot it is. So red is very, very hot, but it's not as hot as it is when it's glowing white. So red are cooler stars. Yellow is hotter. And blue, it's not in order, is very hot. Hot stars appear white or blue as most of their radiated energy is in the blue to ultraviolet range. And cooler stars appear red as their emitted energy is from the red to infrared range in the electromagnetic spectrum. So the colours of stars and hence their surface temperature can be actually used to classify stars. So we have star type, we have the colour, and we have the approximate surface temperature. And this is measured in Kelvin. Now we're talking about very high temperatures, even for the cool stars have very high temperatures. So an O star is a very hot star and it's kind of blue in colour, and its surface temperature will be greater than 25,000 Kelvin. B star is also blue, and that ranges between about 11,000 to 25,000 Kelvin. And then we get an A star, again that is blue, and this time between about 7,500 to 11,000. Then we get an F star, which is kind of whitey blue. and that's about 6,000 to 7,500. A G star is yellow-white, and that's about 5,000 to 7,000 Kelvin. Then we have a K star, which is red to orange, and they're about 3,500 to 5,000. And then finally, cooler star is an M star, and that's red, and that's less than 3,500 Kelvin. Now, the other way we classify stars is by their brightness. Now, there's two ways of classifying classifying the brightness of a star. So the first one is the apparent brightness. So if you were to go out on a clear night and look, you'd see a multitude of stars, and some would be really bright and some would be less bright. So the apparent brightness is how bright the object. Now, when we talk about the brightness of the star, we might also be using this to classify other objects such as planets or moons around a planet. So when we talk about the apparent brightness, is how bright the object is seen by an observer. And this varies by two factors. One, the amount of energy the star radiates per second. Now that's, we call this measurement the luminosity of the star. So the second thing that influences the apparent brightness of a star is the distance from Earth. Now, stars are huge distances apart from Earth. Now, therefore, you can have a star, you can be looking at stars in the night sky, and one can appear very bright and one can appear very dim. But because you're looking at that apparent brightness, the brighter star might in actual fact be less luminous than the dimmer star, because if the dimmer star is much further apart, because it's travelling further through space to get to us, it makes it look dimmer, which is intuitive. Therefore, the apparent brightness is not the most useful method of classifying the brightness of the star. The second method is the absolute brightness, or the absolute magnitude. This depends only on the luminosity. It assumes a standardized distance between Earth and star. So it assumes that the Earth and the star is 32.6 light years away. Which is 3 times 10 to the 17 meters. So it takes a star and it assumes that if that star was 32.6 light years away from the Earth, what would its magnitude be? And so with every star that we classify with its absolute magnitude, you're looking at what the luminosity is at that if the star was at this distance away from the Earth. So you can see that this is a more useful method of looking at the magnitude of the star. Light follows an inverse square law, which means a light source is twice as far away. Oops. It appears 4 times less bright. So the luminosity is inversely proportional to the distance away squared. So let's consider the evolution of stars. Stars are formed in nebula. These are clouds of gas. The gas particles are pulled together by gravity until the center becomes more dense, and this allows a protostar to form. The compression causes gas molecules to increase in speed, and thus temperature and as temperature increases up to about 15 million degrees Celsius, eventually nuclear fusion can occur. Once nuclear fusion begins, the thermal energy generated prevents the protostar from shrinking anymore. once the star uses up its hydrogen, helium fusion begins. Our sun has been in a steady state of fusion for a very long time. So this makes it what we call a main sequence star. After this steady state of fusion ends, the next stage depends on its mass. So as the star gets hotter, it expands. So as fusion occurs and the hydrogen's being fused into helium, and the star gets hotter and hotter, it begins to expand. After a period when the hydrogen runs out, the star's no longer going to be called what we call main sequence star. At this stage, the star starts to appear red. It starts to the surface will start to cool down, and the surface will spread out more, and then we get what's called a red giant. When fusion ends, the outer layers are pushed away, and the hot small core of the star collapses, and it can become a white dwarf. Our sun, although it appears large to us, is in fact quite a small average star. When stars with a larger mass than our sun run low on hydrogen, the helium will then start to fuse into carbon. The star gets hotter and hotter and expands, and as it leaves the main sequence, it becomes a red supergiant. Eventually, these massive stars will explode to become a supernova. The explosion blows out the outer layers of the star into space. These are really quite beautiful things to look at. You should have a Google pictures of them. They're really spectacular. The remaining core of the star contracts, and it may form an extremely dense neutron star. Or if the original star was massive enough, it could even form a black hole. Now, both a neutron star is a star that wasn't big enough to form a black hole, but these are still, neutron stars are really small, but their mass is exceedingly high. A star that can form a neutron star, these are big stars, and that mass just gets contracted right down into this very small space, so they're hugely dense objects. And a black hole is so dense and it's so massive that its gravitational pull is such that light can't escape, and it will begin to it pulls things into it that's in its neighborhood. So let's look at this star evolution. So it begins with a huge hydrogen cloud. And then we get gravity pulls the gas together, and that's what we call the protostar. high pressure and temperatures cause nuclear fusion. And then we have this long, stable period of normal life. And that's where our star is. And we call stars in this part of their lifetime main sequence stars. Energy is released by the fusion of hydrogen to helium for a very long time. Then the hydrogen runs out. And the next stage depends on the mass. So we've got 3 stages that the star can enter into. Firstly, a medium mass star, like the Sun, the outer part becomes cooler, so it will appear red, and we get a red giant. And a red giant, the outer part expands out. So when the Sun enters into its red giant phase, it's actually going to expand into such a size that at that point, if the Earth is still here, the Earth would get enveloped in this massive red giant star and get consumed. But it's not going to happen anytime soon. So so the outer part becomes cooler, it becomes a red giant, but the core shrinks down and it forms a white dwarf. A high mass star so it's a few times more massive than the Sun, carries on fusing helium to other elements like carbon. Then the star forms a red supergiant. Then it explodes, forming a supernova. Then the core will contract down to form a neutron star. Then we get the third class is going to be super heavy stars, and these are many more times massive than our Sun. These stars form red supergiants. So they progress down very much like the stars that form neutron stars. They form red supergiants, then they explode, forming a supernova. But because of the mass of these stars, the core contracts to form a black hole. Just better note here that the huge hydrogen cloud, this is the nebula. Now these stars, we can actually classify them and put them into what's called a Hertzsprung-Russell diagram. So this is a Hertzsprung-Russell, HR for short, diagram. And we can see, now it's important to note here that what would be the x-axis is actually in the opposite direction. So this is the 3000 Kelvin up to 30,000 Kelvin. So here you've got your M stars, then you've got your K, your L, your F, A, B, and O stars down here. And so this is the surface temperature getting hotter, and here is the luminosity. And this is the the luminosity, or the absolute magnitude could also be plotted on this side. Now, here's your white dwarfs that we mentioned. So the white dwarfs are those stars that were kind of just medium mass, ordinary average stars like our sun, and these are sitting down here. So they're not very luminous, and but they're still quite hot. And here is what we call the main sequence, this line here. This is the stars in their longest period of their life, and they'll kind of travel along this part of the graph. So you've got kind of cooler red stars down here, and this is where the sun sits, in this kind of middle-ish region, and it's a kind of yellow, not super hot like the ones over here, but not that cool. So it's nicely down here. And then you've got this kind of breaking away in the diagram. Sirius, one of the stars close to Orion, it will be found about here. In the red giants here, the star Aldebaran is here. That's a nice big red star. You can find that quite easily in the night sky. Up here, you'd find the star Betelgeuse, which is one of the stars in Orion. It's the one that looks really quite red on the shoulder. That's Betelgeuse, and that is a super red giant, and that's going to explode one day into a supernova and look really quite impressive. Rigel, another famous star, nice bluey whitey star that you can see in the night sky, is over here. Is a bright, very hot main sequence star. What this shows us, that when we plot the data for the surface temperature and the apparent magnitude, that stars aren't randomly scattered, but they do form these distinct groups. And we can see, when we look at where a star sits on the Hertzsprung-Russell diagram, we can really get an idea of where it is in its life lifespan and where it's going to end up moving. So I hope that makes sense.